So as we go through the interpretations of quantum mechanics, there's a lot to talk about. The first thing that we need to discuss is this whole idea of a photon being able to go through any slit that it wants, and never mind the active observation forcing a choice. Next, we want to ask the question, when we do force a choice, why does it choose the way that it chooses? If it goes through A, why? If it goes through B, why? Why? And why does it do this half the time and this half the time? And the answer is seems to be that there is no answer, and that this effect of which one it goes through is actually a random effect. Random in the truest sense of the word random. Whenever we talk about randomness, we tend to kind of just mean something that we can't predict the outcome, or we're not sure why it happened. For example, people will refer to coin flips as random. They'll say, oh, well, I just randomly flipped heads, or I just randomly flipped heads again, or I just randomly flipped tails. And so, but in fact, that's not a random thing. It's not random, it's unpredictable, it's chaotic, but it's not random, because we could, in retrospect, go back and we could answer the question, why was this tails? It's tails because I started it out tails, and because I started at a certain angle, I applied a certain force, it went through air, I caught it here, that caused, the air resistance caused it to slow as it spun, and if I had caught it here and then I flipped it over, and you can build a physical model, you could actually build a machine if you wanted to, that in principle, you could build a machine that would flip heads every time. Because it's not random, it's well understood. Even lotto balls, if you have lotto balls coming out, bouncing out, like when you open the door, how fast you have the fan blowing inside, all those things are going to affect the outcome. This is a process for which we cannot affect the outcome. We're going to get a certain answer and we have no control over it whatsoever. It is random. Scientists don't like this randomness. The whole idea of science is to figure out why things happen. So science has had to come up with answers, responses to this randomness. And there's a lot of them. There's libraries built on this single topic, or there could be. Maybe there aren't, but there could be. So, but we're going to just deal with two interpretations today. We're just going to talk about the Copenhagen Interpretation, which is kind of the boring one. This is the interpretation that was kind of championed by a lot of these people that figured this stuff out, the Bohrs, the Plancks, the pioneers in quantum chemistry. They didn't deal a whole lot with this reality question. They developed what we call today the Copenhagen Interpretation, which essentially says that these formulas just describe the world. These formulas that work, that describe quantum mechanics really well, they just kind of work, and they just describe, the key word being describe. They aren't actually telling you some sort of fundamental reality of the world, but they just kind of tell us how things are going to break out. They're going to tell us that it's going to be half this and half that, but they don't say why, and they don't deal with why. They don't really care why. It's just kind of a, don't get too worked up about this whole idea of the cat. Schrodinger proposed the whole cat thought experiment, obviously, and so that was sort of kind of to needle this, or it was actually to actually I don't even know. I could look it up, I suppose, but it may well have been as just an illustration of how ridiculous it is to take quantum reality too seriously. And so the Copenhagen interpretation just kind of says, well, these formulas work, They describe reality. They don't tell us about reality. They don't tell us about anything underlining reality. And this entire idea is countered by one of the most interesting interpretations that you'll ever hear. You might have heard of this before, but you maybe didn't know that it had to do with quantum mechanics. Let's go back to our two slits. And this was touched upon in the cat video, if you did just watch the cat video. The idea is that every observation of a quantum event, every time you collapse a superposition of states, you poof, that's my poof symbol, create two new, well, in this case, two. You create two new realities, one where the photon goes through A and one where it goes through B. And that everything in this universe gets duplicated over exactly the same way in this universe into a parallel universe where everything is identical in the two universes except for this outcome. And then this universe would track on this way and be split and split and split, and this one would track on that way and be split and split and split, until within a few seconds or hours or days you would have, you know, trillions and trillions of, you know, unimaginably huge moles of moles of moles. But we haven't talked about the mole yet in this class, but huge numbers of universes in which every single possible event that was ever possible exists in one of those universes somewhere. And so that is the many worlds interpretation. It's not a theory, it's not been tested. At this point it's a hypothesis, and we'll talk more about it in class, but I wanted to get the basics, the basic what it is and why it's there up on the web so that you could look at that. Get over here. Woo!